Hi everyone. In this video, I'm going to revisit some of the ideas about symmetries in Lagrangian mechanics and hopefully try to explain things more clearly this time. So our first idea was that a symmetry of the system is a transformation of a trajectory, or of all trajectories, that preserves the action of that trajectory. Okay, so this is what we saw before in the last video. Or not the last video, but the last in-person lecture. But we're really particularly interested in the case where our transformations are leaving the Lagrangian invariant itself. And that's sort of a stronger condition that will also ensure that the action of a trajectory is preserved. So we're interested in the case where we're thinking about the same transformation, but rather than considering how the transformation, changes the whole trajectory, we're really just interested in the case where we consider a particular point in the configuration space and then seeing how that transformation then changes where that particular point goes to. So this first transformation, it's of the trajectories. So these are the same transformations in general, but our first view is one of a whole set of points that are the trajectory that are being transformed, and then the action is preserved. And then in the second case, we're going to say the Lagrangian is preserved. Right, so that the Lagrangian is invariant. And this one, the Lagrangian being invariant always implies that the action is invariant. The action of the trajectory is invariant because the action is equal to the integral of the Lagrangian. And so if the Lagrangian is the same, then the action will be the same. Okay. So with the first idea, with preserving the action I talked about, we take a whole trajectory and then transform it. But with the Lagrangian being preserved, we have an equivalent interpretation, but one that still seems conceptually different, which is that we're letting the system evolve until a specific time. That it doesn't matter what time exactly this is, but let's just call it t. And so let's imagine the system is just like one particle. And it kind of just does its thing. Let's until here. So we'll say that, this is let's call this Q of t. This is sort of the point in the configuration space that the system is at, or that the particle is at. And then exactly at this time t, we imagine doing some, performing some transformation, right? The symmetry transformation on this particle. So let's say it's like a translation to over here. And then from here, from this position with the same velocity as it had here, we let the particle continue to evolve according to, the Lagrangian of the system and then the principle of least action. And then it'll do its thing for the rest of time. Okay. So, since the transformation is a symmetry of the system, going between here and here, right? So I could call this Q prime of t. Prime just meaning the new Q of t, not the derivative. So over here we have the Lagrangian of Q of t, Q dot of t, t. And then here, for this particular transformation, we'd have the Lagrangian of Q prime of t, which we know is just Q of t plus some fixed translation vector that let's call A. And then the velocity Q dot we know is the same. And then t. So because the transformation is a symmetry, the Lagrangian is invariant, and so we know that these two are the same. Okay. But the transformation doesn't necessarily have to be a translation. The overall conceptual idea is that we do some transformation so that it transforms both Q and Q dot, potentially, and then the Lagrangian ends up being invariant. So in general, we would have something like this: Q prime of t, Q dot prime of t, and then t. So this is our general situation. Since the transformation we're looking at is a symmetry no matter where or when we do it, we can say that the original trajectory and the transformed trajectory are both physical, just with different initial conditions. Okay? So it's basically like we did exactly the same procedure as before, but for a whole trajectory, we just did it with every point on that trajectory. So we do this transformation that we just did for every point, and that will generate some new set of points. So if we consider the transformation being like a vertical translation, then we get something like that, roughly. Let me just read it. And so, because from every original point to the new transform point, the Lagrangian is invariant, then that means that the action is the same. And so that the action of the original trajectory is equal to the action of the transform trajectory. And so both trajectories are the physical trajectories with their sort of respective initial conditions. So we sort of have this new initial position and then this new final position. And why can I say that they're both physical trajectories? Like, how do we know that this new trajectory is does actually minimize the action? Like, couldn't some other new trajectory with these initial and final conditions minimize the action? Well, I know that this one minimizes the action because if it were some other one, let's use this, that was like this, well then what I could do is I could perform the exact inverse transformation to what I just did before and get a trajectory for my original initial and final positions. And if this one here minimizes the action for going between, these new, Q prime naught and Q prime F, these new initial and final positions, then because this transformation is a symmetry of the system in that it preserves the Lagrangian, that means that the action of this trajectory is the same as the action of this trajectory. Okay? So if the action of this one is smaller than the action, why can't I find colors? Alright, so if the action of this this red trajectory that I've arrowed to is smaller than the action of this one, then that means the action of this one is smaller than the action of this one, which contradicts that this original trajectory minimizes the action between these 2 points. Okay? So whenever we transform through a symmetry transformation, we essentially preserve the physical trajectory, right? It's not going to be of some different form because, well, for the reasons that we just saw. Okay? And if you're thinking, well, we don't necessarily want the action to be minimized, we just want it to be stationary, the point is that the condition of the action being stationary gave us the Euler-Lagrange equations, and the Euler-Lagrange equations give us a unique solution for the trajectory. So what we saw just showed us that, either the trajectories of this color were the physical trajectories, or the trajectories of this color were the physical trajectories. There was no way you could have a mix of the two, because each ones of the same colors were related by a symmetry transformation. Okay, so what is the overall conceptual idea? And this is really important. When we do this transformation at time t, then the system is basically just carrying on just as it normally would have. So I said before that we do this transformation, right, from here to here, and then we let the particle evolve as if it had started at this position, right, with whatever velocity it has. But because it's a symmetry of the system, what that means then is that because there's sort of this equivalence between the physical trajectory it was on and now the physical trajectory that it is now going to be on, the system, the system is just going to evolve in time as it was through this, this original trajectory here, but just transformed a bit after we do this transformation. So if that transformation is a translation, then that means however the system was going to go. So if that looks something like this, or I guess here I said it was going to be, so the system was going to go like this. Well, what happened, I just stopped the system here, right? And then I translated it. And then when I let it evolve, it just did the exact same thing that it was going to do, just at a later position. And that's what happened here. Okay? So we did a transformation to the system that in the end did not change its physical behavior, right? You could imagine that instead of actually transforming the system, what we did as an observer was we changed our coordinates in the exact opposite way. So you could say that, no, I'm not going to include that. That's stupid. So because the transformation of the system is preserving the physical behavior, that is why we consider it to be a symmetry of the system. So when we transform where the particle is and what its velocity is, but relative to that transformation it keeps doing the same thing as it normally would have, we can say that, the symmetry didn't really do anything to the system. Right? That symmetry transformation didn't affect the system, and so it preserved all the physical behavior and really, all of the things that are physically important about the system. So that's why we say that like a symmetry of the action or Lagrangian is a symmetry of the physical system. So this is clearly very important because it's saying we can transform a physical system in some way, and for all, the purposes of physics, nothing changed. And how exactly does that happen? Well, it's through a transformation that preserves the action. And the cases that are very interesting are the transformations which preserve the Lagrangian itself. Okay, so hopefully it's a bit more clear. Then we can start to talk about continuous symmetries. Okay, so this is all building up towards Noether's theorem, so that's why we're talking about this next part specifically. So we're now interested in the case of continuous smooth symmetries. And what exactly do I mean by that? Well, there's a couple things. So the symmetry transformation itself, so if I consider it as phi, which is a function of, well, let's say it goes from m to m, and what this m is the set of all the possible positions that the particle can have, along with all of the possible velocities that the particle can have. Okay, and sometimes this is called the phase space of the system. Right, so when I said the symmetry is a transformation of the configuration space, it's a bit more accurate to say it's a transformation of the phase space. Because given a particle at a certain position, I will also have a particular velocity when it's just moving. And the symmetry transformation tells us how to affect the position, but we also need to know how to change the velocity. Right? If we're dealing with a trajectory, then it's clear how the velocity is changed. But if we're just talking about a specific point along the trajectory, and let's say we didn't know what the trajectory was, then we don't know what its velocity is. Right? When we had the trajectory, we had all of the information to figure out what the velocity is, but in this case we don't. So we need to know how to transform that as well. Okay? But if we knew the trajectory, then we could transform the trajectory and then take the derivative to figure it out. Okay, so we're viewing these symmetries as functions from the phase space to itself. And so for every point in the phase space, so let's say this is Q, this is Q dot. So this would be like a one-dimensional system. then, something like a translation would look like we're taking every point in phase space and then shifting its position uniformly. So I'm not 3 blue 1 brown here, I don't have a way of animating this, but if you imagine just all of the points here in phase space together being shifted by some fixed amount to the right, then that is the transformation that's happening. Okay? So then, one thing that we want in particular, that phi as a function from this phase space to itself is smooth. And what that means, really for us, is that it's just some sort of differentiability condition, right? That we can have all of these coordinates of the phase space. So the coordinates for that describe the phase space would be, each of the QI's and then the QI dots. So we would have, one for each position in the degree of freedom, and then one for each velocity in the degree of freedom. So if we have 3n degrees of freedom normally, in what we were talking about, then we're going to have 6n coordinates for the phase space. And then phi being smooth is saying that at the very least, right, this is not the actual definition of smooth, but what we really need is that we can always differentiate phi with respect to any of these coordinates. Okay? So, that is one thing that we need for these symmetries. Right. Yeah. The other thing that we want to say to talk about the idea of these continuous symmetries is not that the symmetry transformations are each continuous functions. This is something that we already know because we just said that they're differentiable. But what we want to say is that each element of this symmetry group is specified by a single continuous parameter. Okay, so I think last time I said that we can use multiple continuous parameters, and that's perfectly fine. But it turns out with Noether's theorem that it's easier if we focus on these symmetry groups that only have one continuous parameter. And then for when we have symmetries with multiple parameters, we can just break them down into these sort of subgroups that only use one continuous parameter. And then if we describe all the symmetries with just those, then we can build up the whole symmetry group that has the multiple parameters. So for now, we're just going to deal with when we only need one continuous parameter. Okay, so each element is specified by a single continuous parameter. And moreover, we want this parameterization of the elements of the symmetry group to be smooth in some sense. So we want this parameterization to be smooth. And last time I talked about this idea of the symmetry groups being what we call Lie groups, and that itself makes this symmetry group a manifold, which is something that we can put coordinates on and talk about, calculus on stuff, on manifolds and stuff like that. And it sounds all complicated, so I wanted to give an example to show you exactly how this works. So consider the group of 2D rotations. So that's what we call SO2. Is the group of 2D rotations. And I want to consider exactly what I was just saying for SO2. So each element of the symmetry group is specified by a single continuous parameter. So how do we specify 2D rotations? Well, we specify them by their angle of rotation, which we'll call theta. Okay? So every rotation, I can specify what exactly that rotation is for these 2D rotations by the angle that I rotate each point. Okay? And the only case in which they're the same is if these two angles differ by 2 pi, which is okay. In fact, that's going to be important to how we represent this group. Because if we can specify each rotation by the angle theta, well, each theta specifies a point on a circle. Right? Because we can have each value of theta, like each real number value of theta, but we know that if two angles differ by 2 pi, then the rotations are the same. And also, if you consider, let me just use this. Yeah. No. Okay. So, if we consider the central angle in this circle, so if we're looking at this point, we can always uniquely characterize it by the central angle theta, but you have to take into account that you can consider any additional multiple of 2 pi. And that's exactly what happens in the case of the 2D rotations. And so we then have this equivalence between the rotational group, SO2, and this circle. Okay? And the circle we call S1. just a note. And so if we have this sort of equivalence between SO2 and then a circle, then what we can talk about is the smoothness of the parameterization of the circle by theta. And hopefully that is a much more intuitive idea. It's something that's easier to grasp. That as we go along theta, then we go along this circle in a smooth way. You know, in a sense that the circle itself is smooth. Okay, we can verify that this circle is smooth because the computer produced it and not me. And if we want to check it mathematically, that the circle is smooth, well, we could imagine this circle being embedded in the 2D space as it is now. And we have this function that takes the angle theta to the 2D position of the circle. So we have cosine theta I hat plus sine theta j hat. So this is the x coordinate of a point on a circle. This is the y coordinate. And we can clearly differentiate this thing with respect to theta, right? So I'll just write out what it is, but it's not particularly important. And because we have the notion of this derivative, and then we can keep on doing this derivative, we have this notion of the circle being smooth, right? Okay. So then, because the circle is smooth, we can say that the set of the rotational symmetries are smooth, and that through this correspondence between the rotations and then the actual set that is the circle, because the circle is smooth, we can then consider some idea of differentiating with respect to theta these rotations. Okay? So the smoothness here implies smoothness for the rotations. Okay. Now for what we're going to do with Noether's theorem, and also for considering infinitesimal transformations, it's even better if the parameterization obeys the following. And this is something that we can pretty much always do, what I'm about to write. So for any two values of the symmetry parameter, so let's call it R and S. Okay, so if I represent this symmetry done by some parameter R, so you can think of we're doing this symmetry transformation by some amount R, and then I compose it with this symmetry done by some amount S, then it's equal to the symmetry done by the amount R plus S. So this could be rotation, it could be translation, it could be a lot of different things, but whatever it is, the parameter that tells us how much we are doing the transformation has this kind of structure to it in terms of telling us what symmetry it corresponds to. Okay, so this kind of law we can see is clearly true for rotations and translations. So for SO2, if we consider, the rotation done by an angle theta, so we rotate from this point here to this point here, and then, I guess this would be the first transformation we do, and then we do a rotation by theta prime, so we rotate from this point to this point here by theta prime, then this was equivalent to rotating the original point by an angle theta plus theta prime, right? Or theta prime plus theta. Doesn't really matter. So for these one-parameter symmetry groups, we want a parameterization such that when we do these transformations, they kind of build on top of each other in this additive way. Okay? And for translations, you could imagine doing the same thing, where you translate a point by some amount A, and then you translate again by some amount B. Then in the end, what you've done is translate by A plus B. Okay. So this is nice, but what's really important about it is that we can consider infinitesimal transformations. So ones where we're considering the symmetry transformation, but doing them by some infinitesimal amount, which I'll call delta. And then once I know exactly how this infinitesimal transformation works, right? So this is a function of q and q dot for the phase space. Once I know how this works, then through our sort of build-up law, which is what I'm going to call this, this law tells us that we can kind of build up these transformations from one another. I can then use this infinitesimal transformation to construct any transformation that I want. Right? So conceptually, this is a bit like rotating by some really, small angle and just doing it many, many times. Okay? And what we want to do is do each rotation by some infinitesimal angle, and then when we repeatedly do that an infinite number of times, we'll get some whole finite transformation. And we know we can do this because of exactly this condition. So repeatedly composing these infinitesimal transformations, and on and on and on, the transformations will build up in how much we do it. And because these are all infinitesimal at the end of the day, this will give us overall a symmetry transformation that's done by some sort of finite substantial amount. So infinitesimal transformations can then be used to generate so-called finite transformations. So ones that are done by an amount that's not infinitesimal. Okay, and this is what we saw last time. We said that the symmetry done by some amount theta we can think of as composing the infinitesimal transformation phi delta with itself infinitely many times. And a particular case that was worth noting, or makes this a bit easier to think about, is, well, this phi theta, because of our buildup law, is always going to be equal to this phi done by theta over n amount. So n is an integer. And then we compose it with itself n times. This is n times, which we call phi sub theta over n to the nth power. Okay? Then basically what we're going to do is that we're going to figure out in specific cases, so for specific symmetries, what are these infinitesimal transformations? How do they act? And then, once we know that, we can consider any symmetry transformation as this sort of construction of an infinite buildup of those infinitesimal transformations. So we take exactly this thing and then take the limit as n goes to infinity. So taking the divisions of the overall transformation parameter to infinity. So by taking n to infinity implies that each one of these transformations becomes infinitesimal. Okay? So now the question comes to how exactly do we find what these phi delta are? Because that's what we just said we're going to use to figure out any transformation. Well, since the parameterization of the symmetry transformations is smooth, so yeah, since the parameterization of the symmetries is smooth, we can sort of Taylor expand, or not Qi, let's just do Q. We can Taylor expand this symmetry transformation, but not with respect to these coordinates, but with respect to the symmetry parameter. Okay? So, before we do that, I just want to mention again, when I'm writing Q and Q dot without an index, I'm not saying that there's only one of them. Just right now, I'm saying that this is sort of the abstract point in phase space, and I've not yet put coordinates on it. Okay, so you could use Cartesian coordinates, you could use spherical coordinates, you could use some weird coordinate system. But right now I'm just saying that all I'm concerned about are the actual points, regardless of the coordinate system. And that's what I'll do for a bit, until I don't. Okay, so now let's talk about this Taylor expansion. So, and this is where the stuff we did before comes to pay off. So, if we consider Taylor expanding this symmetry about essentially the identity, so when, or I shouldn't have said that, I gave it away, but about when you do nothing, right? You do the symmetry by no amount. So then we first get that transformation. And then what we do with the Taylor expansion is that we take our variation from 0, and then we multiply by the derivative of this thing when we perform our transformation by no amount. And then this is this transformation then is evaluated at the same Q and Q dot. Okay, so we have other terms, but let me just explain more what's going on here. So here, just imagine comparing it to a normal function. You know, when we have f of x and we're Taylor expanding about a, then we start with f of a, right? That's what's going on here. So instead of having delta, we have 0, and here we go from x to a. Then we add f prime of a, so that's this part, and then we multiply by x minus a, which in this case is delta minus 0, which is just delta. Well, then what's the next term in the Taylor expansion? Well, it's 1/2 the second derivative at a times x minus a squared, and then we get, all the other terms. For this infinitesimal transformation, the next term would then be 1/2 delta squared, and then times the second derivative of the symmetry group. So the second derivative with respect to the symmetry parameter of the symmetry group, but at the identity, so when we do nothing. And then that itself is a function that we can evaluate at q and q dot. Okay? And then we get all these other terms. But the thing is that because delta is infinitesimal, right, we're kind of representing it as you know, theta over n, but the limit as n goes to infinity, then delta is so small that delta squared and any higher power of delta is essentially zero. And this is often a practical notion of what we mean by an infinitesimal. It's so small that its square is essentially zero. Right? And if you don't believe me that it's essentially zero, well, I can just make delta smaller, because I have that freedom. Okay? So if delta squared is essentially zero, then this whole term actually doesn't matter then. Which is good, because we don't really want to deal with higher and higher derivatives. So, all we really need is this. Okay, this looks a bit confusing, but let's try and figure out some stuff. So, I've already given this away, but it's worth just showing how it works. So this phi 0 transformation, what exactly is it? Well, we can show what it is through my so-called build-up law. If I take phi 0 composed phi s, well, this is equal to phi sub 0 plus s, which is just s. And then if I do the inverse transformation here, so phi s inverse, this is equal to phi s compose phi s inverse, which is the identity by definition. And this part here is also the identity. And so phi 0 compose the identity is just itself. That's the whole point of the identity transformation. And so then phi 0 is itself the identity transformation. And that should kind of make sense, because the transformation by which we do nothing, like we do it by no amount, shouldn't change anything. And so, as a transformation, it should just be the identity. Okay? So, then what we can say is that this phi delta simplifies a tiny bit. So phi 0 of q and q dot will just give me q and q dot. And then we have plus delta times this derivative. Okay. Okay. So this derivative at theta equals 0, and remember, theta equals 0 is the identity. So this is the derivative of the symmetry at the identity. And it itself is a function of the phase space. So that's why we put in this element of the phase space. Okay? So this is pretty trivial, just this part, because when we're considering phi delta as this function that we put q and q dot into, the first part we just get itself back. And so this is just expressing that when we do an infinitesimal transformation, we're very close to the original point in phase space. How close are we? Well, the scale of our closeness is delta, because this second term expresses our deviation away from where we originally were, and that is scaled down by this infinitesimal parameter delta. Okay? So for an infinitesimal transformation, we are infinitesimally close to where we started. And that all came from the idea that our parameterization for the symmetries was smooth, right? So that's a way you can conceptually think about this set of the symmetries being smooth. So that if I have my phase space, and at each point I do this sort of infinitesimal transformation, it means that I really will just be infinitesimally close to where I started. And the details of exactly how I change my position infinitesimally are given by this, the derivative of the symmetry at the identity. All right? So one thing to note is that even though this symmetry takes in both the position and the velocity, the two don't affect each other. So it's completely fine to think about separately how we transform the position. So let's call this q prime. And then also how we transform the velocity. And if we're dealing with a given trajectory, instead of just a point in phase space, then this thing here, the transform velocity, will just be the derivative, the time derivative of how we transform the trajectory. Or actually, I need a lot of parentheses. And so I put the q of t in here to denote that we actually know the trajectory that we're transforming. And so the new velocity is the velocity of the transformed trajectory. Okay, so what we're going to focus on then is this. And we could have many, many degrees of freedom for specifying the positions of all the particles in our system. And so for each degree of freedom, we can kind of look at the components of this phi delta of q, right? Because what you could imagine is that we're going to get some x prime. So x goes to x prime, which is some sort of, you call it phi 1 delta of q, and then y goes to y prime, which is second phi delta of q. And so these are not powers of phi, but I'm just saying like this is the first component, this is the second component, and we could go on and on. And so for each kind of component, so qi prime, so the specific component of the configuration space, well, what is this if we know that this is phi delta of q, and the kind of ith component of that? Well, phi delta is, I could rewrite this. Phi delta is the identity transformation plus delta times this derivative at the identity. And so what I'm going to call this derivative at the identity, and then each component, right, that spits out, is that I'm going to call this xi. Okay? And that's a function of q. And then this is all times, or this part is times delta. Okay? So let me just go over this a bit again. So phi delta is the identity plus delta times this derivative. So the identity transformation just keeps the point in configuration space fixed. And so if our point Q has components, Qi, so Q1, Q2, on and on and on, then when we do the identity transformation, it'll still have the same components for its position, with these degrees of freedom. So the identity transformation, its components will just be Qi. And then this derivative will act on our position Q, and then what we get for each degree of freedom, I'm calling xi, which depends on the original position that we put into it. And then this is multiplied by delta to express that we're doing this transformation by an infinitesimal amount. And so the position only changes infinitesimally. Okay? So this is the final result that I am particularly interested in. Okay? This as well, but this one is going to be more practically useful. But what's going on here is that the details of the infinitesimal transformation are given exactly by this derivative. And this derivative is explicitly only a property of the symmetry the symmetry group that we're talking about. So this derivative is some sort of part of the structure of the whole symmetry group, and it alone tells us how to do infinitesimal transformations. And then, so we can call that derivative like x, and then x tells us how to do these infinitesimal transformations, and these infinitesimal transformations tell us how to do any transformation. So that's why this derivative at the identity is so important, because it gives us enough structure to tell us how to do any symmetry transformation. So it has enough structure to tell us any element of this group. So it's not just part of the structure, it actually is the whole structure. And this x is what's called the generator of the group, for exactly that reason. Okay? So these x's are going to be particularly important when we do Noether's theorem, which hopefully we'll see today when I come into the high school. Okay? See you then.